Let us begin with the simplest picture. A function of two variables assigns one height z to every point x, y. Imagine the x and y coordinates drawn on the floor. The value z is the height above that floor. When all these heights are joined together, they form a surface like a smooth hill or a bowl. Keep this picture in your mind. The input, x, y, is on the floor. The output, z, is the height. Choose one point on the surface and call it P0. Its coordinates are x0, y0 and z0. The numbers x0 and y0 locate the point on the floor. The number z0 equal to f of x0, y0 is the height of the surface at that place. Now a natural question appears. What does slope at P0 mean when the graph is a surface? On an ordinary curve, there is essentially one forward and backward direction, so one tangent slope is enough. But on a surface, we can leave P0 in infinitely many directions. The surface may rise rapidly in one direction, rise slowly in another, or even fall in a third direction. Therefore, we begin with two basic slopes, the slope in the x direction and the slope in the y direction. First, we want the x direction slope, so we keep y completely fixed at y0. Geometrically, this means placing the vertical plane y equals y0 through the surface. That plane cuts the surface. The intersection is now an ordinary curve lying inside the plane. On this curve, y0 is only a fixed number, therefore z becomes a function of the single variable x. Here is the memory trick for f sub x. X moves and y is frozen. A student may ask, if y is fixed, why can z still change? Because x is still changing, and z equals f of x, y0, so its height can change as x changes. We are moving along the cut curve inside the plane, not wandering freely across the whole surface. The tangent slope of this one variable curve at P0 is exactly f sub x at x0, y0. Start at x0, then move a small horizontal amount called delta x. Before moving, the old height is f of x0, y0. After moving, the new height is f of x0 plus delta x, y0. So the average slope is change in height divided by change in x. It is new height minus old height divided by delta x. When delta x is not zero, this quotient gives the slope of a secant line joining two nearby points. Now let delta x become smaller and smaller. The second point moves closer and closer to P0. In the limit, the secant line approaches the tangent line to the cut curve. Therefore f sub x at x0, y0 is the limit as delta x tends to 0 of new height minus old height divided by delta x. Its meaning is simple: instantaneous slope in the x direction while y is held fixed. Now we want the y direction slope. This time, keep x completely fixed at x0. Geometrically, place the vertical plane x equals x0 through the surface. This plane gives a different intersection curve through the same point P0. On this curve, x0 is fixed while y is allowed to change. The matching memory trick is for f sub y moves and x is frozen. Move from y0 to y0 plus delta y, while x remains exactly x0. The average y direction slope is again new height minus old height, but now we divide by delta y. Let delta y shrink to 0. The secant line approaches the tangent line to the second cut curve. Therefore f sub y is the limit as delta y tends to 0 of f of x naught, y naught plus delta y minus f of x naught, y naught all divided by delta y. This is the instantaneous slope in the y direction, with x held fixed. For f sub x, vary x freeze y and use the plane y equals y naught. For f sub y, vary y freeze x and use the plane x equals x naught. The easiest memory trick is this. The subscript tells you which variable is moving. Here is another important doubt. Does a larger derivative mean the point has a greater height? No, the value z tells height and derivative tells steepness. Height and steepness are different ideas. Consider the smooth surface f of x, y equals x squared plus 2y squared. Differentiating only with respect to x gives f sub x equals 2x at the point 1, 1. The x direction slope is 2. Differentiating only with respect to y gives f sub y equals 4y at 1, 1. The y direction slope is 4. So near 1, 1, the surface rises twice as steeply in the positive y direction as in the positive x direction. Again remember, the derivative is local steepness while the function value is local height. Now we come to the important warning in the textbook. The two partial derivatives examine only two special directions. F sub x checks the x direction, and f sub y checks the y direction. A function may behave perfectly well on those two cuts, but behave badly along a diagonal or a curved path. Therefore, the existence of f sub x and f sub y alone does not guarantee continuity. Consider the piecewise function from the page away from the origin. It is xy divided by x squared plus y squared. At the origin its value is defined to be 0. For f sub x at the origin, move only on the x-axis, since y is 0. F of h, 0 is 0, therefore f sub x at the origin is 0. For f sub y, move only on the y-axis, since x is 0. F of 0, k is also 0, therefore f sub y at the origin is 0. So both coordinate axis slopes exist, and both are 0. Now approach the origin along a direction that the two partial derivatives did not test, the diagonal path y equals x. Along y equals x, the function becomes x squared divided by 2x squared. For every non-zero x, that value is 1/2. Therefore the limit along the diagonal is 1/2, not 0, while the function value at the origin is 0. The x-axis path gives 0, but the diagonal path gives 1/2. Since two paths give different answers, the full two-variable limit does not exist. This is the key lesson. Two good slices cannot control every possible direction on a surface. First, f sub x at x naught, y naught is the tangent slope of the cut y equals y naught. Second, f sub y is the tangent slope of the cut x equals x naught. Third, the subscript names the moving variable. The other variable is frozen. Finally, partial derivatives are directional slope tests. By themselves they are not a complete test for continuity. Now the two textbook figures have one clear meaning. Two vertical cuts through one surface producing two tangent slopes at the same point.